Welcome back to the Advanced R stream. You may have noticed, if you have been tuning in, that I did not stream yesterday, and that's intentional, actually. So I'm trying out this new thing where, in order to make this Advanced R Learn With Me series work with my schedule, I'm trying to only stream every other day now. So I'm going to read chapters on the days off, and then I'm going to discuss material that I read yesterday in the up and coming day. And so yesterday, you guessed it, I read chapter 3, and today we're going to talk about chapter 3. If you're new here, welcome. This is the Advanced R Learn With Me series, where I go through the material in the Hadley Wickham's Advanced R book, sort of at a gracious speed, and I invite people to join me as I sort of talk through the contents of each of the chapters, as well as in real time try to solve the exercises, and then I'll check with the answers and talk through some of the solutions as well. And so we'll do all that here. Last time we finished chapter 2 on names and values, and now this time we're going to start a new chapter on one of the most important sort of data structure in R, that is the vector, or data type. The vector is everything, and you'll notice that the vector comes in a lot of flavors. Specifically today, we're going to talk about 2 of the flavors, and you'll see, or what we'll get to see as we go through the material today, is that vectors are everything that we know of in R, really. And the sort of material or the common data types that you think of, like data frames or even the new Tibble, are really just flavors of the vector. And things like matrices and arrays are even just vectors to R, for as much as R is really concerned on the deeper level. But they're the vectors with bells and whistles, and we'll talk about what these bells and whistles are, and really what they are, and to give you like a purview, is they're called attributes. So attributes is like the special data that comes with the vectors. So before we get into that, let's just break down the most important features of the chapter today. So we have a vector. We're going to talk about 2 types of vectors. We have an automatic and a list. Lists, and actually there's a third one called a null. But it's not a vector. I guess it's a generic length 0 vector. But lists, or otherwise known as generic vectors, are a vector with a special characteristic, that is that, well, I guess it's easier to explain the characteristic as how it deviates from a vector. Vectors are elements, well, a set of elements that are all the same types. And that's sort of the notion of atomic kind of comes from here, where like the atom is supposed to be like I don't know physics, so mind my like lay physics here, but the atom is supposed to be one of the principal sort of components to what makes up everything. And so I guess I don't see the reference here. Maybe we should back out of that reference. Let's just remember atom. When I think of atom, I always think of like consistency. And maybe this is also because of that James Clear book, for those of you who know, it's called Atomic Habits. So it's like the principal habits, or like the bite-sized sort of bit that I can look up what atom is, right? Oh, well, of course it knows it's the smallest unit of ordinary matter. Look at that. Funny enough that the user interface for programming comes up. Oh no. Video quality not the best. Dang. Frowny face. Me too. It's something I tried to alleviate from last time. I tried to like optimize my configuration in OBS, but so I'm trying one trick at a time. I think currently this is definitely better than how it was last time I was streaming. Oh, but it looks like it says I'm getting 30 frames per second. That's terrible. So maybe before I dive too deep into this content, yeah, I think that's where my stream is right now. I'm gonna have to move my setup, I think. Where my room is does not help my situation for my stream setup. But thanks for the note, chat. Let's see if I can. I don't think I can mess with this while I'm live. I like closed everything out today. I thought, oh no, I should be better. And you know, technically it says I'm in the green on stream quality, but that's with respect to 30 FPS, which is very bad from my YouTube investigations on stream quality. But we're gonna run with it because it's 11:30 and I have to stream today, so here's the material, irrespective of quality. It's about getting it out there. And if it gets out there and it's a mess, then that's how it is out there. Great. Okay. So where were we? Right. That's where we were talking about vectors and the bifurcation between the two like basic data types that describe vectors. And the first is atomic. The second is lists. What's crucial to remember here is just that an atomic vector is going to have all the same type. So, you know, we know what those look like, right? We can think of those off the top of our head, but like when we do these sorts of like lists, like what makes this what it is, or if we like looked at I might be thinking of MATLAB right now. No. Right, it's a numeric and a numeric vector, right? So if we send it to a project here. Oh, I took away. I don't need it. Boom. Right, it's gonna give us this value here that we bound x, like we learned last chapter. We bound x to this concatenated series of inputs here, these values, and this is a vector, a numeric vector to be exact. An easy sort of way to make this something different, and we'll talk about. Now it's an integer, but we'll talk about these sort of differences. But what's, I guess, crucial at this point is just to all the elements in this concatenated set of values are the same type. They're all integers, right? And you notice there when I made one not an integer, it coerced the vector so that it was a number. So now these two are numbers. When we talk about this sort of like sequence or hierarchy of coercion and how it has implications for when you're creating larger data structures like data frames. And specifically, it's actually some of the motivation for why the Tibble, another new vector on the scene, was created in order to alleviate some of the issues with coercion from data frames. Anyway, so how do we get all of those flavors of some of the things, those data types I was talking about? Well, you build off of either atomic or list vectors using attributes. And you can think of attributes as these sort of characteristics that are tied to the vectors. And in most cases, the attributes that are going to be always tied to a vector are going to be its dimensions and its class. And I believe you can access the attributes for a given reference object by doing this. So no attributes here. Maybe we need to be more, because it's not really anything. Maybe I wonder if I can make this, give me some attributes. None. That's a good example. I guess we'll get to some examples in the chapter. But if I made this like as dot data frame, for example, this kind of gets at, and then we'll make x equal this, y equals this, okay, equal that. And we have the attributes here. So we have the names, we have row names, which is just one because it's one observation, so it's just one row. And then we have the class. And we're going to dim. It's dim of x 1 1 because we have 1 by 1. Interesting. This isn't a 1 by 1. I guess it turned it into there. But if I did this, now I have 3 variables. Now it's gonna give me the names. We have x, y, and a, right? It tells me this class, and then I have the row name, but row name is 1 because we just have 1. The dimensions on this are 1 by 3 because I have 1 row and 3 columns. Right, so you're starting to see some of this metadata underlying this very simple reference value pair. Cool. And really, that's going to be important when we get into more complex structures that have all the bells and whistles related to them. Like when you think about a model object. So in linear regression, you save the model object, right? Well, this model object has, what makes it different than these principal structures is all of the bells and whistles, these attributes that are attached to it in such a way that give it sort of special characteristics and allow you to manipulate it and use it in a variety of ways so that it also abides by the rules set by R. So that's cool. Looks like there's a little quiz here we can try if we want. So what are the 4 common types of atomic vectors? Numeric, integer, logical, and numeric, integer, logical character. Rare types, I would say like NA maybe. Is it a rare type? or it's like complex maybe, I don't remember. Attributes are like the metadata. I just went on lengths describing what attributes are here. How do you get them? How do you set them? Well, I was just playing with it. You get them by attributes. You set them by attributes, if I'm not mistaken, or assign or something like that. What we'll see in the chapter. How is a list different from an atomic vector? It's the variability in the elements. So atomic vectors are homogeneous in the sense that all elements are the same data type, while lists can be any data type, even lists themselves. So you can have lists nested within lists. How are matrix different from a data frame? Well, matrix could be technically a data frame, and we'll see cases of this. But if I'm not mistaken, it's the elements within the data frame. So a data frame is made up of lists. A matrix is an atomic vector with additional dimensions. So all the elements in a matrix are the same. Another characteristic, if I'm not mistaken, is that matrix have these features in maths that make them transposable. However, data frames, when you invert them in certain ways, you're not going to get the same thing if you did this like double inversion in the same way that you would with a matrix. So can you have a list that's a matrix? Yes, you can. Can you have a data frame, have a column that is a matrix? Yes, you can. It's very tricky to do, and you have to make sure that it also abides by the structures or rules of what is a matrix, but we know that a data frame can have, we know if it's the case that a data frame is just a bunch of lists, and we know that lists can have matrix in them, then data frames can have matrices. So how do tibbles behave differently in data frames? Those, I don't think I can name all those off the top of my head, but some of this speaks to what I was talking about earlier, where some of the coercion protocols for tibbles are different, where it's not going to make variables into character strings, for example, or it's not going to recycle So another feature of data frames is that if you try to assign a data frame where this was a different length than this one, then it's going to fill in a specific way. So for example, I did like this 1 to 5. Now my first one is 1 to 5, but this is 1. So what happens when we do this? Oh well, the data frame still runs, but what does the data frame look like then? Well, we can see 4 filled all the way down, 2 filled all the way down, this went all the way to 5. Well, this sort of behavior doesn't always work how we would hope it to behave, and in fact, in some cases, I wonder if I'm good enough to make it break. I think in this case, yeah. In this case, I can get it to break here because it can't do this recycling procedure. A tibble, on the other hand, would not break here. It just wouldn't let me do. Let's load the tidyverse. If I'm mistaken, it just won't let me do this, or it recycles in a different way. Yeah. So it gives you some errors, but it gives you some very helpful errors. Right. So that's one difference that we'll talk more about. I think the chapter calls tibbles like what is the name? They'll yell at you more, but they'll yell at you in ways that'll help you in the long run. So you should listen to the warnings they give you. So they're noisy. They give all these warnings and stuff, but the warnings are supposed to be helpful. But they essentially in a lot of ways, they're very similar to data frames. Okay. atomic vectors. Look, here we go. These are the 4 atomic vectors that we talked about. Logical, integer, double. Oh, a double. I didn't talk about a double. I just said numeric generally. But a double and integer and the fit within numeric, which is an atomic, which is a vector. So here's 4 primary types of special syntax, aka scalar. So creating an individual value we'll call a scalar. One thing to note about scalars though is that while they have a different name, technically a scalar is just a vector length 1. Or at least that's how R actually handles it. So if I were to do something like x, and then I would assign it the value of 1, for example, and then I ask, is the vector of x, it should give me true, because this is a vector while it's representative of a scalar. For example, if I wrote true here, like a boolean, we can ask if this is a vector, and it's going to give me true, right? Because look at the structure. It's an atomic vector. But if I'm not mistaken, I think this vector is not what we think it is. It produces a vector. Returns true if a vector is a specified mode having no attributes other than names. Oh, so interestingly enough, in order to do this sort of if-else statement about assessing the characteristics of some reference argument, it's just looking at its attributes. So in this case, we looked at the attributes that are null, so it's going to give me a true on the vector. That's kind of cool. We'll get what I'm playing with that. Make longer vectors with C, so C is short for combine. I always thought of C as actually being short for concatenation, but call it what you want, bro. Oh yeah, we went through some of the types here. You might be wondering what's the difference between a double and an integer. Well, a double is going to have these decimals. Integer is just like a single value, sort of like in maths. Well, just like in maths. But I don't know if we call things in maths doubles. I think that's just a computer science thing. I'm really trying to crush content tonight because I want to get off by midnight. So I'm really only streaming for like 15 more minutes. And then I'm really going to have to dive in on the next day. But I think a 2-video series for each chapter is a fair depiction. So maybe if we can get to like these exercises here, that'd be great. Or if we can get to attributes. Okay. So the inputs here to a concatenation are always atomic vectors. That's interesting. So if you put like a big one here, then this concatenation is just going to double combine here. So we're always going to get atomic vectors. And then we can check that by violating it by doing lists, but we'll do lists when we get to lists. Okay, so here's how he'll depict vectors in the diagrams. They're these rectangular blocks, and you'll notice that each of the elements in the vectors, right, are going to be the same one. That's very important. You can check what type of variable or data type a given reference is to by looking at type of missing values. So it's a note here about this little conversation about missing values. An NA is different than an NaN, right? Because NaN was like a special data character, right? A null, sorry. Right, a null is a special type of data structure, but an NA is a particular value that, when within vectors, has nasty sorts of behavior. We can even add an A here, right? A data frame. Warning, data frames deprecated, use the tibble. Notice that I wasn't getting this warning before. I get this warning now because I have tidyverse loaded, so anytime I use data frame, tidyverse smartly sends me this little warning that I should switch over. It's still telling me an error though. Oh, because the difference in size here. Now we got an NA, so now we'll get like a bunch of NAs. NAs have this weird behavior. Like I couldn't take the mean of X right now. Mostly because there's an NA. And when NAs are in the mix, they're infectious. On computation, they'll just like eat everything up. NA here, NA, NA. NAs beget more NAs is the no. So this is particularly salient when you're working with missing values or missing data in a data analysis context. That was actually something that I was working with today. Today I spent a fair chunk of my day working on a diversity, equity, and inclusion project where we're doing a climate survey. So if you don't know what that is, we're essentially surveying the members of the department that I'm a part of in order to get a sense on the social climate. So sort of how people feel they're being treated, are there particular things that they would like other people broadly in the department to know about or have knowledge of, and sort of inform departmental level decision making moving forward, and give knowledge about to the public about sort of the quality of interactions of members of the department, which I think is important to keep us accountable for our behaviors. But anyways, the point of this was that in analyzing some of the survey data, there were some NAs, and I was actually getting a lot of headache today trying to figure out how I could write some plotting code that properly addressed the NAs when I was summarizing the data. And so that's like basically the point of that is just like NAs come up. You're bound to run into them. There's not a perfect sort of scenario. So knowing what to do when they come up, or knowing the types of implications for having them on, or how they behave or interact with other data structures. Important. Cool. You can check NAs. SNA is kind of an interesting function, right? Because in most cases, when you interact with NAs, they throw more NAs. But in this case, NAs is a acceptable input because it's supposed to be identifying the NAs. Okay. And then there's a bunch of NA types. Okay. Testing and coercion. Generally, you can test if a vector is a type by saying is. I just did that over here. Is vector, for example. Avoid is vector. They don't test if you have a vector. So, like I said, this doesn't test if I have a vector, it looks like. It tests if there are any other specified attributes. So it's going to let me know if it has more than the attributes that we normally have. So in this case, right, we have a table, data frame. So that's its class. So this is class. Then we have row names, and we have names. But if it was a vector quote, it would just have names. And I think that's what this vector is. Okay. So here's the string of coercion hierarchy that I was talking about, where characters to doubles to integers to logicals. In this case, everything becomes a character. If we get characters, everything's becoming a character. That's the idea. Doubles, integers. Which is why earlier in the example I had the 3 integers and I changed one. So we could predict what this is going to be based on the hierarchy here. We know that if I change one thing to a numeric or double, right? If I change one thing to a double, then the integers are going to go up the ladder. I'm going to look at class. We know what this is. Another interesting thing, say if I had a true here, the class is numeric and this becomes a 1, which is cool. But if this was an integer, I think they become integers. So this becomes an integer 1 if I have a true here. Another cool thing. But if this was like an F, then everything's becoming a character, right? So this is the level of coercion for variables. And this is going to have big implications on when you're bringing together variables, when you're getting outputs from certain models and stuff. Some outputs come in certain forms, and there might be like unnoticed coercion going on, and here, it can happen automatically. So a lot of functions coerce to numerics, and a lot of packages, when you use these sort of arbitrary functions, you'll get outputs, and the outputs might not correspond to the data types that you were working with, and now we've got like this hodgepodge of potentially coercive data structures. I like saying it like that, like coerciveness of an output changing or manipulating what you put in. And then things might break because of this. I think is the more important thing. Things might break. Okay. Let's keep going. Coercions. Generally, you can also do coercion yourself. There's explicit coercion. So like what I had before as data frame, right? Oh. Okay. Nice. We're at the 30-minute mark. We're at midnight. We're going to do these exercises and we're done for the night. Okay. How do you create raw or complex scalars? Oh, these are the 2 rare data types that we didn't talk about, so we should take a look at them. So a raw vector, you just use raw, or you can use as raw or is raw. A raw type is intended to hold raw bytes. It's possible to extract subsequence of bytes and replace elements. So this byte representation, I'm not sure what it's useful for, but roll 2. So working in raw, not really clear to me why you would want to do that, but it looks like you can create it and identify it in the same sort of ways that we described for all the other data types. With that being said, I'm sure the same thing goes for complex, but complex might be like maybe a complex number? Nice. Well, the cool thing about complex numbers is they actually have applicability for, some of the things that I'm interested in, but we don't have to get into that, but supports complex arithmetic. That's kind of cool. So you can get the real and imaginary numbers. So this is actually very applicable to, what's this code? Wow. So when you're doing the sorts of time series analyses that I'm interested in, so I work with a type of brain signal known as electrocephalography, and or otherwise known as like EEG. So you might have heard of it like this, but essentially what it's capturing is synchrony of postsynaptic potentials, and we're doing so using scalp electrodes. And I guess the point to take from this is that when you're pre-processing this sort of signal, one fairly coming about as more common than not approach of doing so is to use standard signal processing tools. And when you're doing signal processing, one way in order to make assessments about the magnitude and phase of a particular frequency of signal is to use complex numbers and like Euler's formula, and move from the complex space back to the move from the imaginary space back to the real number space. And by doing so, you'll get unique information from the signal. And so I imagine that some of the new packages I've been messing around with, I imagine that some of the new packages I've been messing around with actually use this complex data type more frequently than not. So maybe that's something to look into, and I'll circle back and check with people on that. That's kind of cool. But yeah, so complex is probably less common, but it is cool to see that sort of functionality available in R. So you can get real, imaginary. Yeah. What does this mean? It might be complex conjugate or something. Complex conjugate, yeah. Complex conjugates are one thing that you can use to extract amplitude information from a signal too. It's like a quicker way. Then like you could take squares of values, but okay. That's gonna be like too much deviation. Interestingly enough, we can use complex numbers, which is kind of cool. Test your knowledge of the vector coercion rules by predicting the output for the following ones. Okay, here we become an integer, or if this is a numeric, it doesn't have an L next to it. So here we're going to become a double. Here we become a character. Here we become an integer. And that's sort of just what I was playing with before. We can like write these things down too. And we can look at the classes for each of them. Numeric, character, integer. Cool. Why is the default missing value NA logical vector? What's special about logical vectors? Hint, think, false, NA character. Why is the default missing value NA? It makes me think about, is that function is NA again, but I'm not sure that that's where the answer lies. True, false, they're ones or zeros. Excuse me. my guess here is because if an NA is an NA, it's like easy to contain an NA. False NA. It's true. True NA. What is the class on this? It's character. I don't know. What precisely do is atomic is vector. This okay. So we looked at as vector. As vector is going to test for mono attribute data types from the arguments passed to it. Is atomic. Is an object atomic or recursive? So an assessment of recursive like structures. So is atomic. Gonna test if it's one of these. Most are regarded as exceptions are the atomic types. No. So maybe some intuition can be developed. Is this atomic? That is atomic. Okay, but if the data frame is that atomic, it's not atomic. That's a list. It sort of helps. Okay, what about the last one? Is numeric. Is numeric creates. Is numeric. Internal generic primitive function. You can write methods to handle specific classes of objects. It's not the same as this double. Factors are handled by the default method. Should only be true if the base type of the class is double or integer and values reasonably regarded. So if the base type is numeric or integer. Let me think of a cool example then. So let's start. Oh, it should be false in this case, right? Because we have this. But if we make x equal one or something. True. Atomic vector. I was thinking about like this. More restrictions. Okay. Let's see what advanced are. So tell us about some of these questions that were a little more ambiguous, or at least ambiguous to how I answered them. Okay. In our scalars are represented as vectors length 1. However, there's no inbuilt in syntax for logicals, integers, doubles, or characters to create individual raw complex values. You have to create them this way. Character to raw complex. Imaginary numbers, yeah. Okay, got those right. Okay, here's that. Oh, this is a different question than I just read, right? Oh no, I skipped it. Why is 1 equal to 1, 1 true? Why is -1 less than false? True, because false is equal to 0. A character is true. Why is 1 less than 2 false? Because any character string is equal to some set of values. Is 1 or something. These comparisons carry out operator functions which coerce their arguments to a common type. So if we're doing coercion here in the common type, this gets coerced to a character, so it's going to be true. That's why. In this case, coercion is going to happen where this becomes a character. And then we're going to count characters here, right? False is represented as 0 and 2. Turns out 2 turns into 2. Numbers precede letters. And 2 turns into 2. Numbers precede letters. So this is not larger because numbers would come before letters in the character sort of hierarchy of coercion, or magnitude, maybe, like ordering, ranking. Why is this? Okay, the presence of missing values shouldn't affect the type of object. NAs with atomic vectors. So NAs get coerced just like anything else. So being illogical gives it like the lowest rung of coercion. So if you start as logical, then you become a character. You can become, you're like chameleon-like in terms of like what you will become coerced into. Okay, so last question then is numeric, is vector, and is atomic. Atomic tests if an object is atomic vector or is null. So it's either atomic or null in this case. Say is numeric tests if an object has an integer double type and is not class of these types, which are sort of building off of the basic numeric types of integer and double, because a factor, as we'll see soon, is integer, fancy integer. Is vector test if an object is a vector or an expression that has no attributes, and we learned that earlier in the chapter. Cool. So that's what we got to today. Today we reviewed the atomic vectors and the common data types here of the vector atomic. We talked about some of this motivation for the distinction that is to come when we break into lists. But next time we're going to talk about attributes. It's the sort of dressing or frosting that comes on all of the data types that we'll talk about. So data structures are just, as we'll see, are just building up off of these initial structures, but adding characteristics, metadata to them in such a way that we now can interact with them differently. So that's going to be really cool to see, and there's going to be a lot to come out of attributes and exploring attributes and managing your attributes or seeing how they become managed for you as you reference or bind names to different types of objects or sets of values, data types. I'll never get that straight. I'll call it like 20 things. Anyways, thanks for tuning in today. Have a great night. I'll see you guys not tomorrow, but unless I might get surprise stream myself, but I'll probably see you guys on Wednesday. Yeah. All right. See ya.